Good morning and welcome to the physics video lecture. This is Physics 105A video lecture 33. Today we're going to talk about the Kepler problem and work our way all the way through it. See how far we get. Good, so what is the Kepler problem? We have everything set up for this now. It's a central force problem. It's a reduction of a two-body problem to a one-body problem. It's the orbits of the planets around the sun and everything that goes along with that. So let's see where we should start here. We'll list all of our ingredients briefly. We have the equation of motion. That's a central force problem. Here, F of R was minus alpha over R squared times the unit vector. So the minus sign meant it's attractive. The alpha is a positive constant right here. And potential energy, so just minus alpha divided by R. Okay, with the potential energy, we had a conservation of energy. So I'm going to go ahead and write down the energy. We had 1/2 m r dot squared plus 1/2 m r squared p dot squared plus u of r is equal to E. So we had conservation of energy. We had conservation of angular momentum. So let's go ahead and write this out. Conservation of energy. Okay. And we had conservation of angular momentum. We had L is equal to m r squared phi dot. Conservation of angular momentum. We had, of course, gone into the plane polar coordinates at this point. And when we put these two things together, let's go ahead and send this up. Right, when we substituted phi dot up here with phi dot from down here, we had ended up with 1/2 m r dot squared plus L squared over 2m r squared plus u of r, and we're already, yeah, let's go ahead. Equals E. Keep it in the general form for a moment. So this is what's referred to as the effective potential. And at this point, we're at a one-dimensional problem here that we're going to integrate. Next thing we're going to do is integrate. And of course, the u of r here is the one up there, minus alpha over r. So we're going to integrate this differential equation. It's first order, and it's just a single variable r. So let's go ahead and do that. So next, integrate equation star, and it's using separation of variables. Separation of variables. Okay, we're going to use separation of variables here, and there's our dr dt. So let's go ahead and write it in two steps. Dr dt, that'll be plus minus, we'll have a square root. So there's a 2 over m, and then there's E minus u of r. I'm going to go ahead and plug in the plus alpha divided by r minus L squared over 2mr squared. Okay. And to get the time, we could write dt is equal to dr divided by this expression here, 2 over m plus alpha over r minus L squared over 2mr squared. And we'll keep the plus minus here. So yeah, we would integrate both sides. We'd have t as a function of r. This would be an integration variable r prime. And then if we could invert that, we would have r of t. What we're looking for, though, explicitly is the equation of the trajectory. So, to find the trajectory, right? We're looking for Kepler's first law. We have to get phi as a function of r, and what we're going to do is replace this dt with the dt out of that. So we're going to use L equals m r squared d phi dt. So if we just substitute dt for this dt here, we've essentially used the chain rule and made a substitution. So we would have dt is equal to mr squared d phi over L. Okay. That's all we're going to do. We're going to make that substitution and then continue with the separation of variables. Okay. So we have mr squared over L d phi is the dr divided by this thing right here. So we're going to get phi on one side and r on the other. Or phi is equal to a plus minus integral. Okay, so we've got the L dr over mr squared divided by the root 2 over me plus alpha over r minus L squared 2mr squared. Okay. So we have to do this integration now, and these are all primed for what it's worth. So that's the form of the integration. This will give us phi of r, and if we can do this, we're going to invert it and turn it into r of phi. So yeah, this is the point where I want to dump this whole thing into your lap collectively, because this is an integral everyone has to have done. So I just want to make sure we have it set up right. And there are numerous simplifications, but basically we have to do this integration, make sure I didn't miss any algebraic step here. And what we're going to find is, as we simplify it, it will eventually turn into an inverse cosine. An inverse cosine with a pretty complicated argument. Okay, so let's start to simplify this thing. Before I leave all the final steps up to you guys. Okay, I'm going to consult. Yeah, I have this this is fine. We got the plus sign, we've got the minus sign there. Yeah, okay. So first thing to do, and here's what we're going to do. We're going to call this homework. So the first thing to do is to retrace all these steps and make sure you really agree with this thing, okay? Make sure we haven't made any errors here. And then we have to do a couple of substitutions to turn this into something that's easier to work with. So here, integrate. Because yeah, this Kepler problem is one that we want to have done every step and really understood every step. So one thing you can do is, you've got that phi, you can just pull out the L over M in the numerator and the root 2 over M, right? We'll deal with that later. You've got the dr over r squared, and you've got this E plus alpha over R minus L squared over 2mr squared. Okay, so there are a couple of substitutions that will lead to the goal, right? Deal with those things out front later. First thing, okay, get into this form. So there's a U substitution, let U equal 1 over R. And by the way, we still have a plus minus here. U, let U be 1 over R. du is equal to minus 1 over R squared dr. Leave some room in your notes too, so that you can insert that in there at the right time. So what do we have now? Just in terms of that integral, okay. Don't want to deal with these right now. 2 over m. We have the dr over r squared. And we're still going to have a plus minus, minus plus, plus minus, doesn't matter. So we're going to have the du there. We're going to have the root E plus alpha u minus L squared over 2m u squared. Okay. Now at this point, you could actually go into an integral table and find your inverse cosine. You can go to the integral table, find your inverse cosine in terms of all of these quantities here. Or you can continue doing some substitutions. Yeah, I'll let you guys find the substitute. You can continue doing some substitutions. You're going to complete a square down here. You can actually bring it into this form, dw over root 1 minus w squared. At which point you really know you've got your inverse cosine. Okay. And then you work your way back with the substitutions until you are right here. Okay. So this is what I'm going to leave you guys to do. I want you to do this homework, this integration, any which way, until we get this result here, and that's where we're going to start. So what we end up with is, okay, so this is homework. Next, you know what, I'm gonna put an intermediate result here. I'll put an intermediate result just so that you know what we're looking for. You get cosine phi is equal to u minus alpha m over L squared. Or you get phi equals inverse cosine of this. This is what your substitutions will bring you back to. 2em L squared plus alpha squared m squared over L to the fourth. Okay. So this is what my substitutions bring me back to. Inverse cosine of this, and then I take the cosine of both sides. And this we want to solve for. Okay, your substitution, you're going to put the u is equal to 1 over r in here and do a couple more algebraic steps. But if from here on out it's just algebra, you're going to end up with r is equal to p over 1 plus e times the cosine of phi. I had this up on the board the other day as the polar form, except now we're going to know what these parameter and eccentricity are. So this one's L squared over m alpha, and yeah, so this one is L squared over m alpha. This is the square root of 1 plus 2el squared over m alpha squared. Okay. And this is where I'll pick up again with the whole discussion. Good. And as, yeah, so I just put the box around here, and we'll leave this up for a while and I'll work on the other board. So this is what happens when you've worked your way through. We have to now make heads or tails of this. This is the polar form of the conic sections. But you see, it's not just a geometrical formula, because all of our physics is built in here. This angular momentum, this is the alpha is the constant on our potential energy, so we know it contains masses and Newtonian G and everything. Energy, again, alpha, angular momentum. So yeah, these quantities contain all of the physics, polar form of the conic sections. So we have to work our way through this now and figure out and you know, prove Kepler's laws, right? This is the Kepler problem. So yeah, this was homework, namely to make your way to this integral, make sure you understand it. I've given you a couple steps. There are a couple different ways to do this. You're going to end up with this, okay, after having found this inverse cosine and, you know, all of these quantities. That was an alpha squared m squared, right? That's a 2. So what we're going to do next is the analysis. By the way, this won't take that much. You can leave space in your notes and fill it in as well. What we're going to do next is analyze these results here and get Kepler's 3 laws and more. Okay. So that's the formal calculation. So let's consult the clock here. Good. Okay, so from the polar form of the conic sections with these quantities here, right, our energy, our angular momentum, our Newtonian constant there, the mass. From these we want to find Kepler's 3 laws. So Kepler's laws. The first thing we have to do, we have R of phi, so we have to remind ourselves that we were in plane polar coordinates. We went from Cartesians to plane polar coordinates. So of course we know that x is r cos phi, y is r sine phi. We want to graph this in the xy plane. And let's go ahead and do it right here. I did draw that beautiful ellipse for you once. This one will not be as good. But what do we have here? We have when phi is equal to 0, right, x is equal to r, and when phi is here equal to 0, we have r is equal to p over 1 plus e. So what we have here is p over 1 plus e. And then when phi is equal to pi, cosine of pi is -1. So over here, we'll exaggerate this a bit. We have minus p divided by 1 minus e. Okay. Because we're over on the left side there. So r is equal to p over 1 minus e, and we're on that left axis, so we put the minus sign in front. Okay. What about cosine? What about phi is equal to pi over 2? Right? Then x is 0 and y is r. And that means we're right up here. Phi is equal to pi over 2, and it'll be symmetric. And it will just be equal to p. Right? P over 1 plus 0. So this is p and this is minus p. And I'll take this as enough points. Let's make this a little higher. P minus p. Got a freehand draw this. We're coming up. Not bad. Okay. Okay. Now notice that the geometric center of the ellipse is somewhere over here. And so this is not the maximum height, but rather part way up, but the maximum width or height of the ellipse is up over here somewhere. So we're going to have to find that as well. But so far, we're recognizing that we could have our semi-major axis here and our semi-minor axis right here. And as far as the semi-major axis goes, we have that. So what will that be? So we'll have, for the semi-major axis, we'll have the 2a is equal to p over 1 plus e. Plus this magnitude here, right? So plus p over 1 minus e. That'll be p times 1 minus e plus 1 plus e over 1 product of these two minus e squared. Minus e plus equals 0, 1 plus 1 is 2. So what we end up with is a is equal to p over 1 minus e squared. So that's a relation, that's the semi-major axis, and p is equal to that up there. So we're just going to keep working our way through. We have to find the semi-minor axis next. So next, semi-minor axis. This one's a little trickier because we have to locate the angle at which we obtain this maximum here. So let's make some room on the board. Or should I well, I'll write these smaller. We need a little room here. Okay, so for the semi-minor axis, we'll work the left side of the board here. For the semi-minor axis, we have to find out the angle at which y is equal to a maximum. So we have, once again, semi-minor. We need y maximum. So what is the maximum value of y? What we do is we take y equals r sine of phi, and then we use our definition of r, so that is p sine of phi over 1 plus e cos phi. So this is y as a function of phi. We differentiate it, set the derivative equal to 0. dy d phi is equal to p cos phi over 1 plus e cos phi plus p is sine of phi. Then I have 1 over this, so I have a minus 1 plus e cos phi squared, and then the derivative of e cos phi would be minus e sine of phi. So this is the expression we have to set equal to 0. So equals, I'll put it on the common denominator, 1 plus e cos phi squared. P is out there, so we have cos phi times 1 plus e cos phi, so cos phi plus e cosine squared phi, minus times minus is plus e sine squared phi. And when is that going to be equal to 0? We're going to have cosine phi plus e equals 0, because we have cosine squared plus sine squared is 1. So 0, comma, when cos phi plus e equals 0, or when cosine of phi is equal to minus e. So cosine of phi is equal to minus e. What do we do with that? We plug that back into y. So y max, and here I'm going to collect these in a slightly smaller form. Squared. We have to repeatedly use these things. So r is equal to p 1 plus e cos phi. Okay. So we have everything up on the board here? Yes, we do. We're looking for y maximum. What is y maximum equal? So now y max is equal to r sine of phi is equal to p sine of phi 1 plus e cos phi. Now, put the p out front. We have cosine phi is equal to minus e, so we'll get rid of the sine by writing root 1 minus cosine squared phi 1 plus e cos phi. And now we can make our substitution. Root 1 minus e squared and in the denominator we have 1 plus e times negative e, so also 1 minus e squared. So that is p over, when all said and done, 1 minus e squared. So it's y max. Let's go ahead and write that down. Or y max is b 1 minus p over root 1 minus e squared. E over root 1 minus e squared. Good, so we can collect that result. Oh, you know, I'm gonna erase some of this because we're, okay, we have A, we have B, we have this already. Excuse me. We're back. That was nothing. Okay. We're ready to formulate Kepler's third law. Let's pull all this together now. We have A, we have B. Semi-minor axis. Okay, I'm just going to gather all those results. There's the calculator. I'll gather all the results right here in some nice form. So x and y, let's go ahead and write this. R is equal to P 1 plus E cos phi. There's our L squared over M alpha. E is equal to root 1 plus 2E L squared over M alpha squared. And then we'll fit in the B and the A as well. Yeah. A and B now. So A is P over 1 minus E squared. B is P over root 1 minus E squared. So yeah, we have everything here. Put some boxes around here. And polar coordinates. There is that result. What we're going to do next is continue this analysis. Those are the complete list of ingredients now. Everything up here. There's that picture. This I can erase. Actually, we are missing one thing. So I had this little red star here to indicate the geometric center of this. So that's one thing we have to find here. I'm going to call it D. What is the value of the distance from the origin that we're using for our polar coordinates to the geometric center? Okay. There's a couple of ways to get that, but really it's just going to be easiest obtainable from just taking 2a or 2a minus this distance right here. So I'm going to put that as homework as well. Let me consult the clock. Good, so what we want is the distance from the origin to the geometric center, because we're ready to prove Kepler's first law. Now you could just say, well, this is the polar form of the ellipse, but we really want to get it to the x squared over a squared plus y squared over b squared. So homework. Show that this thing right here really satisfies the equation of ellipse. Satisfies the equation of an ellipse. Now, is that simply x squared over a squared plus y squared over b squared equals 1? Careful. This would be a mistake because we have to shift the origin. We have to shift the origin, so it's actually going to be x. So this is not right. Okay. We have to shift the origin to this point here that you guys are going to find. And that's going to be x plus d, quantity squared, a squared, plus y squared over b squared equals 1. In other words, your new origin is over at x equals minus d. So, x minus negative d squared. That's what we have right there. So, by the way, this d is also going to be expressible in terms of these quantities. So this is the one we're giving as a homework as well. And I'll warn you right now that there's nothing difficult about it. It can be easy to get lost in some of the arithmetic. Okay. What you do is your x and your d is also going to be proportional to this letter p here. So when you're setting this thing up, you cancel out p from the numerator and the denominator. It will cancel out completely. Okay. For example, your a will be p over 1 minus e squared, b p over root 1 minus e squared. And then your x and your y, because they have p in them here, right, or cos or so p, they're also going to cancel the p out. So make sure p cancels out of everything before you continue on with this. So once you get this thing here, then you can really declare victory. Okay, then we have Kepler's first law that these orbits are actually ellipses. I want to use this form because we're going to continue on with this form here, right, the basic form. We're going to continue on with this as we talk about the second and third law. Right, remember it was expressed in terms of semi-major axes and so forth. So we do actually have to have this form. So we won't consider it demonstrated to be satisfying Kepler's first law until we convert this back into the Cartesian coordinates and show that we have this right there. So yeah, first you have to find out what the distance is from the geometric center to this origin. And it's pretty basic. Okay, it's pretty basic. It's proportional to E. Yeah. Good. I'm going to consult the clock once more here. I'm going to go through with Kepler's second and third laws, and then we actually have to return to this and analyze a bit, what it means. In other words, what is the meaning of these various parameters in terms of the way the orbits function? But we have we have everything in place to talk about Kepler's law, so we're going to do that. So this would be Kepler's first law. So let's talk about Kepler's second law. Kepler's second law was the law of areas. In fact, we'll get us an interesting result here. Kepler's first law, that was that homework problem up there. Just a matter of, algebra arithmetic. Kepler's second law. It's the law of areas, and you'll remember the picture we had where this area here and this area over there on the far side are equal. Well, what we can do is the following. We're in plane polar coordinates. We write d area in the sense of a 1/2 base times height. It's 1/2 r times r d phi. So what we're saying is dA dt, which is 1/2 r squared d phi dt, is constant. And I'll put a question mark there. Constant. Well, we know that L is equal to m r squared phi dot. So that would mean dA dt 1/2. Now r squared phi dot is equal to L over m. Right? R squared d phi dt, r squared phi dot equal to L divided by m. L is a conserved quantity. Equals constant. So what that means is the conservation of angular momentum is something we already had, right? We had conservation of angular momentum as a property of the central force problem, and it turns out that that means that the area that's being swept out is constant in time as well. Good. So when Kepler found the second law, though, all of his dynamics had not yet been invented. Conservation of angular momentum was not yet a quantity. So that proves it. So Kepler's second law we already had, in other words. It was just conservation of angular momentum. Camouflage, so to speak. So that's given. Let's go ahead and get Kepler's third law. We'll leave everything up there. Yeah, and these two x's here, this is not to be done. I'll even draw some x's through there. If I'm warning you away from this, it's because I've made that mistake before myself. This is the one that you have to, this is the one you have to do your calculation with. Okay. So Kepler's third law was the law of periods. So Kepler's third law. Now there, we're going to take the area of the ellipse. First we're going to take the period of the orbit, and we're going to relate that to the area of the ellipse. So the period of the orbit, t, is equal to the integral of dt 0 to t like that. Okay. So how are we going to relate that to the area of the ellipse? Area of the ellipse would be the integral of dA dt over one period. Okay. But we do have, well, we just erased it, we have dA dt is equal to L over 2m, L over 2m yeah, dA dt was L over 2m, so we have L over 2m as a constant, and then that was pulled out, dt would be the time right there, okay? So, this on the other hand is pi times a times b, that's the area of an ellipse. So now we just have to write L over 2m t pi times a. Now where is b? If you take the square root of a, so if you take the square root of a, we have a to the 1/2 is equal to p to the 1/2 square root of 1 minus e squared is equal to b divided by e to the 1/2. So b, b here, b is equal to p to the 1/2, a to the 1/2. So a to the 1/2, p to the 1/2. And this already suffices. I'm going to let you guys clean that up. Here we have t proportional a to the 3/2. So t is proportional to a to the 3/2, therefore t squared is proportional to a cubed. So Kepler's laws 1, 2, and 3 are satisfied in this problem here. So you got p to the 1/2, and p itself can be expressed in terms of L, M, and alpha. Okay, so you can actually pull that square root of p out of this thing and then have a couple of other constants. Okay. Good, so that's Kepler's third law. Okay, good. That's where we're going to leave it. So we have Kepler's 3 laws. We have this whole apparatus. You guys want to do that integration, show that this thing satisfies this ellipse here after figuring out what D is. It's just E times A, but I want you guys to find it. Okay. So find out what D is. And then the rest of the laws I gave you, or we derived here. What we're going to do next time is revisit all of this and understand our orbits. Right now we just got the laws out, right? 1, 2, and 3. But we're going to go back and revisit everything and understand the orbits and some of their properties. Okay, good. See you then.